Hello, statisticians, here with lesson one of the T inference procedures. Lesson one is covering the one sample T interval. Let's jump into it. So a couple things to know here. Why are T intervals necessary? This is one thing we want to take away here. And then to be able to complete all four steps of a T interval process, which would be the kind of the 4 points on an AP exam as well, which are the parameter, the type of interval, and the conditions, the calculation, and the interpretation. You'll find the parameter is the one area that is semi-optional. A lot of times intervals are 3 points with the bottom three being the points. But the parameter, I think, is a good thesis statement to be able to get into the process cleanly and to make sure that the reader knows exactly what you're going to be doing. So a couple things to know first. Again, just the idea of an interval, and sorry, this got cut off up top here, but the idea of an interval is we are in this situation getting a bunch of samples over time, right? And so what an interval is going to do is take a snapshot at one of those samples. And so as you can see here in this picture, this is 7 different X bars, right? And the X bars are not going to be the same because every sample is unique. And so you can expect, even if the population is the same, if it's height of students in our school, if you ask 30 students how tall they are, the average height of those 30 students will rarely, if ever, end up being the exact same, especially if you're getting into, partial inches and things like that. If you're rounding to whole inches on the heights, then you're probably going to end up with some X bars that overlap, which is why the curve ends up looking like this, because the X bars that are closest to the mean happen a little more often. But what happens here is you see we get all these different X bars. We have no idea where mu is. The whole idea of an interval is that we are using the X bar to estimate mu. And so we actually don't know exactly where these X bars lie in the curve. But what happens here, and what gets hammered out a lot of times in multiple choice questions on the AP exam, is the notion of what does a 95% confidence interval mean, for instance? And what a 95% confidence interval means simply is that if we took a bunch of intervals with random samples from the same population, we would, in the long run, for instance, if we had 100 intervals, about 95 of them would cross over the mean. And so you can see here, all the red ones have crossed over the mean. This one green one did not. And so in this case, 6 out of 7 captured the true mean. How do we know if it captured the true mean? We don't really know because we won't know mu ever unless we take a census. But what we're doing is establishing a process where we're a certain level of confidence that we're going to capture the true mean, which is the idea of election polling, for instance. There's always that margin of error, but they may not capture the exact percent who are going to vote for that candidate. And in fact, if it's a 95% confidence interval, we're basically accepting that 5 out of 100 times on average, we will not capture the true mean. So we'll report out an interval and say that the average height in our high school is somewhere between 5'8" and 5'9", and it might actually be 5'7" and a half. But 95 out of 100 times, we will capture that. And so if it's 5'7" and a half, our interval will contain 67 and a half inches or 5'7" and a half within the interval. So keep that in mind. That's this process. We don't know when. Basically it's binary in terms of it either captures the mean or it doesn't. But we do know, and again, just to be clear, it's not that necessarily that any single interval has a 95% chance of capturing the mean, because it basically does or it doesn't. What the 95 refers to is over a period of time with a bunch of intervals, we would expect 95 out of 100 to capture the mean. So that's a subtle difference, but that's really kind of in the proper language on this one here. So let's jump into what these intervals look like then. So a couple disclaimers about the T distribution. First of all, it is a density curve. It's bell-shaped, like we've been working on. It's not quite as pretty as the Z curve. The Z curve is a little taller and a little skinnier. So if this is the Z, then the T might look something like this. And what happens is the T, as n increases, okay, so as n goes up, the T gradually gets closer and closer to the Z curve. So it may start out like this in the T, and then eventually it gets very close to the z. And we'll talk about that. That has to do with what's called degrees of freedom. Um, but as you can see here in bullet point 2, the spread is a little bit greater in the t curve, but it does start to approach that z as the sample size gets bigger. And the reason this happens, and this is an important one, is right here. Okay, the reason the t is not quite as accurate as the z is because the t uses s, which is a sample standard deviation, okay, which is an estimate of sigma. So again, S is an estimate of sigma. So this is the actual, okay, standard deviation. If we took the entire census, this S is an estimate of the standard deviation from a sample. So just that little bit of uncertainty tied to the S versus the sigma is what causes that curve to be just a little wider. So the question that's commonly asked is, what's the difference between a T and a Z? The difference between a T and a Z is the T uses S, the Z uses sigma. And so that little bit of uncertainty in the S is what causes the T to be a wider curve, to have a little more area in the tails, okay, and a little less area in the center. Okay. So here's an example. In an effort to understand the amount of time Minnetonka High School students spend on social media per day, a researcher asked a random sample of 50 MHS students. Okay, so N equals 50. The mean of these 50 was approximately 96 minutes. So again, the mean of the 50, okay, so that's an X bar. Okay, and the standard deviation of those 50 was 23 minutes. So that's an S. Again, it's important to recognize what's an X bar and what's a mu, what's an S, and what's a sigma. But again, keep in mind, if it's a sample, it's an X bar. If it's a population, it's a mu. If it's a sample, it's an S. If it's a population, it's a sigma. What we are trying to do with this information is we are trying to estimate this value. Okay, we're trying to estimate what the actual mu would be. So obviously we got 96 minutes in our sample, but we can't be certain that 96 minutes is exactly how many minutes Minnetonka High School students would or do spend on social media each day. So what we're going to do is report out a range of values that we are 95% confident will actually capture the true mu for the high school, which could be 92, it could be 100, it could be 103, we don't know. But what we're doing here is basically saying we think it's 96, give or take this much. And that's what our estimate is. Again, at no point are we going to make a claim that mu is exactly some value. Okay, that's not our job. Our job is to basically throw a dart to get close to what mu would be and to report that out. Okay, so we've got this information. Okay, so the first step is this idea of the parameter. So we want to define in context the mean that we are estimating. So what we are doing here is we are estimating the mean amount of time an MHS student spends on social media per day. Okay, again, we can get away with not writing this statement, but then we have to be very clear in the end what we are writing about, what we've worked through, what question we're answering. So for me, I prefer to write this up front so that the reader knows basically here's my thesis statement and then here's the work to follow. So the second step is the typing conditions. And sorry, the conditions got cut off here, but there's really two or sometimes three, depending on the importance of bringing up one more condition. But the first condition is always that it's an SRS, okay, that we have some sort of random sample. Eventually, it's either a random sample or randomization in an experiment if there's two groups. But right now, it's just about the sample we've collected. Two is that the sampling distribution can be considered roughly normal. And for our purposes, there's really three ways that we can do that. One is it will tell us, Okay, it will say in the question that either the population is normal or the sampling distribution is normal, um, or something even more specific, like we graphed it and it looked pretty symmetric, and so it's fair to believe it's normal. A second way we can learn or answer this is if n is 30 or more. Okay, if n is 30 or more, then we know the central limit theorem can kick in and assure that normality for us. And so that's what happens in this case. But the third way now, and this is different from proportions, is we could actually create a graph of the values. Okay, and a graph of the values most commonly used is probably a box plot or a histogram. And what we're trying to accomplish with the box plot or the histogram is to show that there's no big outliers. Okay, so even if our sample was 15, as long as there's no big outliers, then the sampling distribution would probably still be roughly normal. Okay, now if the sample was 10 and there were big outliers, then we probably would not solve the idea of the sampling distribution needing to be normal. So again, what this has to do with is understanding sampling distributions and the idea that we're going to graph all these X bars. And if there was some value way out on the outside over here, we might end up getting X bars that are skewed to the right. Okay, and that means we can't run the T procedures because the T procedures revolve around the idea of having a roughly normal T distribution or sampling distribution here. So, so one of those three ways will be used to verify condition 2. The third condition that you'll see sometimes is this 10n is less than capital N. And what this is really trying to do is say we have independence within our sample. And what that means is if we are talking about Minnetonka High School, we are picking names out of this bucket without replacement. And so we're technically changing the probability that somebody gets selected. And if we do that too much, then we're going to start to have a more influence within our sample, and they'll start to be considered related more so. Whereas if we just take 50 students from our high school, it's probably going to be 50 unique students. Maybe they know each other, but they might not be directly affecting their social media usage or things like that. So what we really want is students in our sample who aren't influencing each other. So they're just kind of their own standalone student with respect to their contribution to our data. Okay, so what 10n is less than capital N basically recognizes is the idea that we're taking less than 10% of the population, which is what this means. Less than 10% of the population is in our sample. So basically we've taken a small enough slice of the pie to trust that our individuals in our sample are independent from each other. Okay, and so that's what the 10n is less than capital N. That's rarely been a big point of contention on the AP exam, but it is something that's important to just know in the background. What we'll focus on here really are the first two conditions because those are essential. So in this particular problem, we are going to run a one sample T interval. Okay, and you can identify this by name or by formula, which we'll get to here in the next step, but the formula looks like this. Okay, doesn't matter. Typically students will write it by name, but the formula works as well. But what happens is if you identify this by name, then you actually can get out of writing the formula even with the values when we get there. So I'll talk about that shortly. In terms of conditions, the first one is a random sample. In order to verify this, you would just note question states, quote, a random sample, of 50 MHS students. Okay, so you're literally quoting the question in that situation, and that's how you verify the random sample. Okay, the second condition is about having a roughly normal sampling distribution. So in this problem, n equals 50, which is greater than 30, of course. So sampling distribution is roughly normal. We always say roughly or approximately is roughly normal by the central limit theorem, okay, is assured by the central limit theorem. Okay, then the third one, if we were to talk about independence within the sample, we would note that there's 50 students, and so that 50 students is less than 10% of our student body. And so that assures that independence. So essentially we've got check, check, and if we needed it, check on that third one. But again, first two are the biggies. So the actual calculation, okay, the X bar again is that sample mean, which in this question was 96. Okay. The T star is a value we get from a chart or from our calculator. There is a function on on a lot of our calculators that's an inverse T function where we could get this, but most of you will probably use the chart. And the chart is a laminated pink sheet that we have in class. And in this case, there were 50 individuals. And the way degrees of freedom works is you take the number of individuals in our sample and subtract 1. So what you would say here is degrees of freedom equals 50 minus 1, or 49. Now, if you go to our chart, you will find that 49 degrees of freedom is not on the chart. And degrees of freedom are along the left side of the T chart. And since 49 is not there, we can't go back up to 50. That's assuming accuracy we don't have. So we actually have to go down to 40 degrees of freedom. And I'll talk about this here in a moment, but what 40 degrees of freedom at 95% would be is 2.021. And what that really means is our interval is going to go 2.021 standard deviations in either direction. Now, just to be clear, you do not have to write this value if you don't want to, because again, this value now changes our degrees of freedom to 40. Okay, but presumably you will use your calculator to calculate this interval, and your calculator is going to use 49 degrees of freedom. So what you can do is never really write this T star value if it's not on the chart exactly as you need it. Okay, so what I mean by that is 49 degrees of freedom is not on the chart. So rather than rounding down to 40 like we're supposed to, just write T star if you write the formula. That way you can still use your calculator, which is going to use the 49 degrees of freedom instead. Okay. The S sub x is the standard deviation. And the standard deviation here was 23. Okay. And the sample size, or n, is 50. Okay. So when we get into calculating this, what it would look like is 96 is the X bar, plus or minus. So again, I'm just going to write T star. If we used our chart, it would be 2.021. Okay. And then it's S over root n. Okay. Now, on our calculator, what we can do is stat tests, and this is a T interval, which on mine is number 8. Okay, so I would go down to T interval, and it asks for data or stats. Data would mean you have a list, okay, of numbers. We don't have a list of numbers here, we just have the stats, and so I would keep it on stats here. My X bar is 96, my S sub x is 23, my N is 50, and my confidence level is 95. What that does is that gives us an interval of 89.46 to 102.54 with 49 degrees of freedom. Now again, it's using 49, the chart used 40, so if you're going to write this number of 2.021, that means you cannot use your calculator, because the calculator is using a different T star value, so it's going to get a slightly different answer. So you just have to make sure you're consistent on that. But you are always allowed to write T star. In fact, as long as you have identified that this is a one sample T interval, you actually don't need to write the formula at all if you don't want to. So this part on the AP exam is actually optional if you've identified the type, if you've ID'd type, okay? And so what we have there is our interval with the 49 degrees of freedom that we took from the calculator. Now, what does that interval mean? 89, 46, 102.54. Here's what we do with that interval. We simply write an interpretation, and an interpretation of this interval can be very kind of formulaic in terms of its, there's a certain, you could write it 100 different ways, but there's a certain format that is relatively easy to follow that can kind of cover this for you. And it's this right here. So we are blank % confident that our interval contains the true mean what? And so in our situation here, we are 95% confident that our interval, which runs from 89.46 to 102.54, contains, and now again it goes back to that original parameter, our thesis statement. What does it contain? It contains the true number of minutes MHS students spend on social media per day. This is not a spot to cut corners in your writing, so just make sure you write the complete sentence. That took, I'm still under a minute on this slide, so it doesn't take that long. But you do have to write that full sentence. And so again, what we're saying is we're not positive, but we're 95% confident based on the method that we use this, that if we just kept producing intervals, that in 95% of our intervals, as long as they're random samples and so forth, we'd capture mu. And so we're pretty confident that mu is somewhere in that 89.46. Oh, sorry about that. 89.46 to 102.54 interval. Again, if we wanted to get that interval narrower, well, then we'd have to either lower our confidence level, which means we could use a smaller net and be, have a better chance of missing, if you will. More confidence means using a bigger net, so it's kind of counterintuitive. Higher confidence level actually means you'd have to widen this interval in order to make sure you capture it. But the other big way to improve this interval and to lower its margin of error is to increase n. Okay, so if we want a narrower interval, if we want it to be narrower, the best option is to increase n. Okay, the other option again is to lower the confidence level, which seems counterintuitive, but lowering the confidence level means it's okay if we miss, so we can use a smaller net to begin with. So lower the confidence level. But again, the process here of interpreting this is writing this sentence. You can follow that format. It's good to understand what it means as well. That makes it easier to write it. But as always, if you have questions, please ask. Thank you for watching.